Hello, sir.
Yeah,
Can I ask a question? Yeah,
of
but
course.
the questions they have given you, we don't set your priority within the questions because the question like A is 100110010101. So the
Yes.
first one must be your priority. You must set it as a priority before you work with the other one, or you will not set anyone to priority.
It
Or is it
doesn't really matter if the first one or the last one is used for the parity bit. So
the
it,
first one must set it as a priority bit.
mm, no. So it is given there that you received these patterns and they had been encoded using odd parity.
So you don't need to set your priority bit within this one.
So that's what you received. These patterns are what you receive. And encoding these patterns, an odd parity method was used.
Okay, and I told you must set your priority bit within this one before you calculate for the odd priority.
No, the parity is already calculated there, and the pattern was transmitted, and what you're seeing here is what you received.
Okay, thank you.
Come on.
I have a question, please.
Yes, please go ahead.
An SSD of, like, for example, 256 gigabytes is never exactly that amount of storage. Is that due to the fact of the error correcting? The
No, because
payload is not.
because the error correcting is included in the storage. It is due to the manufacturing process. So you're manufacturing that on a in general, you are manufacturing that by using a material of absolute purity and placing there a wrong particle. That's how you're producing these integrated circuits, so the wafers. So you are wasting your pure material, and that's a chemical process. And you cannot control this chemical process by 100%. And we are talking about a few particles per million. That's the range of. So it is not always absolutely sure that you can produce that with such a high accuracy that each cell that you are building is really working. Is that clear?
Oh, I see. Thank you.
Welcome. So that's the same, for example, from Intel, this Core 7 or this i7 and i5 processors, right? So Intel is separating there between i5 and i7. And usually, so as I understood, they are produced together in the same line. And then after you are doing a kind of benchmark tests with these processors. And the better ones are becoming the i7. Those who are less good are becoming the i5 processors. And better and less good means just the consumption of power if they are calculating something. So let's look into that problem and let's solve that one. So we have here 5 different bit patterns, and all of them was transmitted and was encoded using an odd parity. So what we have to have is an odd number of ones. If we are counting now here, we have 1, 2, 3, 4, 5 ones. So 5 times 1, and that's odd. So that's a valid pattern. In the next one, we have 2 times 1. That's even. So that's a wrong pattern. Then we have 0 times 1. That's also even. And by that also a wrong pattern. Then we have 3 times 1. Odd. A valid pattern. And 8 times 1. Even. A wrong pattern. Clear? Okay. Then let's look to the next question. Could errors have occurred in a byte from the question above without your knowing it? So, is it possible that you're interpreting a pattern as correct even if it is not?
Yes,
And why?
because it check only odd parity, odd parity pattern. So if it is even, if there is a even parity is wrong, it will not know. So we will focus on the odd parities. So if there is if there's even parity, which is wrong, you will not detect.
Right. So, what are other opinions?
There are 2 errors. It couldn't be possible to.
I will just prepare polling, then you make a poll. So is it possible that there is an error that you did not mention, or is it not possible? So up to now, 12 voted, which means all the other 31 participants are just recording, which would be highly illegal according to German law. Ah. So 16 voted now. That's 42 minus 16 is 36. 26. So overall, 1/3 is saying that it is possible. 2/3 are saying it is possible. 1/3 is saying it's not possible. It is possible. Why? The only thing we are checking is if there is an odd number of ones in the pattern. So if we are sending out with an odd number and during the transmission, the signal is interrupted, then would change. But if we have more than one error during the transmission, then it can be that even 2 bits are manipulated from 0 to 1, and then we would have again an odd number of ones, so an odd parity by that. So it is possible that there are errors in the byte that you are not knowing. Is that clear? Okay. Then let's continue with the next problem. How would your answer to question 1 and 2 change if you were told that even parity had been used instead of odd? So the same problem like before, but now with even parity. What would be different? Think on for a few minutes and then let's discuss. So there is one answer in the chat up to now. So let's look into the bit patterns would be the same, but now, and we are again counting the number of ones. So even if we have even parity, that does not mean we are counting the number of zeros. We are just counting the number of ones, and that has to be even now. So let's just copy that one here. So the first one, we would have an odd number of ones. So that's correct. In D, sorry, even. So in the second one, we would have an even number of ones. In the third one, and in the last one. So these three are correct, and these two are false then, if we have an even parity. So here, be a bit careful. If you're counting here the number of ones, that's 0, and that's even. Clear?
Sorry, how is no one even? Like, how is 0 even?
No. For the parity, you are counting the number of ones, right?
Yeah.
And if you have an even parity, then you have to have an even number of ones. And 0 is an even number. If you're dividing 0 by 2, then it's 0. It's even. You do not have a rest.
Okay.
If you're dividing 3 by 2, then you have 1 remainder 1. If you're dividing 0 by 2, it's 0, and the remainder is 0.
Thank you.
You're welcome. So any questions to that?
Hello?
Yeah.
So, but the zeros there are 9. So if you count, they are not even. The zeros there
No,
are
but
9.
we are not counting the zeros. We are counting the ones. Even if we have an even parity, we are always counting ones, not zeros.
Okay. Thank you.
Then the next problem. Construct a code for the characters ABCD using bit patterns of length 5 so that the Hamming distance between any two patterns is at least 3. Who can explain what Hamming distance means? Then let's look into if you don't know. Is it here? Here is the definition. So the Hamming distance between two bit patterns is the number of bits in which the patterns differ. For example, the Hamming distance between the patterns representing A and B in the code there is 4. Between B and C, it is 3. And you should now construct a code for the characters A, B, C, and D consisting of 5 bits with a Hamming distance of at least 3. Please try that by your own for 10 minutes, and then we will look into. So let's look into that's a bit trial and error. There is a method how to create a bit pattern with a certain Hamming distance, but I don't want to present to you because that's really quite complicated. So the easiest is really to do a trial and error approach, I would say. Problem 5. So the first thing that you can do, so we have A, B, C, and D, and you're encoding them with 2 bits usually. So 0, 0, 0, 1, 1, 0, 1, 1. And now you are adding to your 2 data bits 3 parity bits. And let's start just with the easiest combination. Let's maybe space 0, 0, 0, 0. So that will be our start point. Now, between A and B, we already have a Hamming distance of 1. So 1 bit is different. So we need 2 more bits.
Excuse me, sir.
You're not
We
seeing.
can't see you.
So let me start with that. So I just encoded A, B, C, D with 4 bits for the moment. That's what I did up to now with a classical pattern. And now I'm adding to this 2 data bits 3 parity bits. And I'm starting with A with 0, 0, 0, 0, 0, the first pattern. Now, between A and B, for the moment, we have a Hamming distance of 1 already, but nevertheless, the next one shall be 1, 1, 1. Now I have a Hamming distance of 4 between A and B. The next one that I can add is 0, 1, 1. And we still have here a Hamming distance of 1, 2, and 3 between A and B. And to the last one, I'm also now adding such that I have a Hamming distance of at least 3. I have here, for the moment, a Hamming distance of 1. Now I have a Hamming distance of 2, of 3, and of 4. And now let's compare and maybe adjust a bit if necessary. So to compare, you can write the bit patterns here like that if you want. So on the diagonal, we will have, of course, a Hamming distance of 0, because it's always the same symbol, so we can directly fill in 0, 0, 0, 0. Then if we are comparing, so here we have A, B, C, D, B, C, D. If we are now comparing A and B, the Hamming distance is 4. You see they are different in 4 bits. So here we have a Hamming distance of 4. If we are comparing A and C, we have a Hamming distance of 3. There, there, and there. The 2 zeros are identical. And if we are comparing A and D, then we have a Hamming distance of 3. Then we have to compare B and C. There we have a Hamming distance of 3 as well. And we have to compare finally B and D and C and D. So B and D, we have a Hamming distance of 3. And C and D, we have a Hamming distance of 4. So we always have a Hamming distance of at least 3 for this bit pattern. And there are other solutions as well, because we created here 4 different bit patterns, but with 5 bits, you can create up to 2 to the power of 5 different bit patterns. That's one possibility to do that. If you want, you can look a bit into how to create Hamming code, but it's really not so easy, I would say. If you're creating Hamming code, then you are using some bits as data bits and some bits as parity bits, and not each parity bit is including each data bit. So not a simple problem, I would say. And then the last problem for today, you're May starting and you are trying to solve the rest by your own till next week. So using the error correction code described below, decode the following words. So we received some bit patterns and we have to decode them. Let me just copy this original table here and paste somewhere. So the first bit pattern that we received was 1 1 1 0 1 0 and 1 1 0 1 1 0. And now we are comparing what we received with the original table, and we have here 1 1 1 0 1 0, and that's H. So we have here exactly the same bit pattern. So we have here an H. Now 1 1 0 1 1 0, you are not finding in the table. But what you can do is now, let's do the first one very detailed. Therefore, let me enlarge that a bit. Like that. So we found that one here. It's H. And now we are comparing the second bit pattern, the 1 1 0 1 1 0, with the individual lines that we have there. And what we are noting is the Hamming distance. So comparing the pattern with A, what is the Hamming distance here? 4. Comparing with B, the Hamming distance is 1, 2, 3, 4 as well. Then with the next one, it's 1, 3. Then here, the Hamming distance with D is 1, 2, 3, 4. With E,
1.
it is 1. With F, it is 1, 2, 3, 4, 5. With G, it is 2. with H, it is 3. So now the one with the smallest Hamming distance is that one here. So the E, that means we are replacing the received bit pattern by an E. Clear?
Yeah.
And you can now do the same with all the other patterns and identifying what you received there for the rest of the lecture. And then maybe next week we are checking the results.
Sir, when do we have the mock exam?
I guess a week before the exam, so at the very end of the semester, after we are done with the lecture.
Okay, so like we'll have all the chapters in that
In the exam or in the mock exam?
mock exam.
Yeah. Let's see. It also depends a bit on the time if we will have time for a mock exam. If not, then we are not doing a mock exam.
Okay, sir, sorry to disturb you. Can I see the number 1 and 2 question again? Just briefly.
Sorry, there.
Number 1 and 2 question. Also,
That 1 and 2.
yes. No, not this one, like the previous one before the
These 2.
Yes. Thank you very much.
You're welcome.
Professor, one more thing. Please, this last one you just solved,
Mm-hmm.
can you just bit confused how you actually got this? Can you just make a brief rundown again, please?
So what we are doing, we are receiving bit patterns and we are comparing that with our decoding table. And now we are seeing here in our decoding table, we are not finding this bit pattern here. But we know that it was encoded such that the Hamming distance between all the patterns should be at least 3. Now we are comparing the received pattern with the original patterns and seeing that for E, the Hamming distance is 1. For G, the Hamming distance is 2. And we are opting for the smallest Hamming distance to replace our received bit pattern.
Sir, I have a question, not related to the topic.
Go ahead.
Sir, is it possible to cover all of this in like 1.5 months? Because I've missed a lot of classes for this subject.
That's a question I can't answer. That's a question that you have to answer. I don't know. I don't know your pre-education in that. I don't know how easy or hard it is for you to understand things like that. So no any idea. I don't know.
So like what's the passing marks for the subject?
Usually it is for each exam the same, so you have to know at least 50% to pass an exam.
Okay, sir.
So here you are seeing the solutions for the received text. May you are trying by your own to come to them. Then thank you for today. And next week we will review a bit this last problem and then continue with exercises addressing the Boolean algebra.
Thank you.
Thank you,
Thank you.
sir.
Bye.